Hello everybody, my name is Mehdi and my presentation is about an explicit reference governor for time-varying linear constraints. Consider this dynamical system is in general a nonlinear dynamical system. X dot is equal to f of x and v. Here x is the states of the system and v is the reference. We assume that this system is pre-stabilized. By pre-stabilization, we mean that for any constant reference, the system asymptotically converges to the corresponding equilibrium. Since the system is asymptotically stable, then there exists a Lyapunov function, v, which is a function of x and the auxiliary reference, such that the Lyapunov function is lower and upper bounded by two proper class K functions, and the negative of the time derivative of this Lyapunov function is upper bounded by a proper class K function. We assume that the pair x and v is the pair of the state and reference is subject to a set of time-varying linear constraints. If we denote the admissible domain at time t by t dt, this set of linear constraints can be shown via these linear inequality. Here, beta, theta, and omega are proper and time-varying vectors and matrices. We assume that the constraints are bounded and the rate of change of the constraints is bounded as well. So it means that beta and beta dot, theta and theta dot, and omega dot are bounded. Also, we assume that the admissible domain denoted by dt is convex and simply connected with non-empty interior at all times. Here we have a geometric interpretation of the considered class of constraints. Here the solid lines are constraints at time t1 and the dashed lines are constraints at time t2. As you can see, the constraints are evolving over time, but the admissible domain shown in white here is convex and non-empty at all times. Here is the problem that we want to study in this paper. For the described system, which is subject to the described time-varying linear constraints, we should provide an auxiliary reference denoted by Vt such that for a given constant desired reference, the constraints are satisfied at all times, and the auxiliary reference tends to the desired reference. In order to solve this problem, we will use the explicit reference governor framework. Explicit reference governor, or ERG in short, manipulates the auxiliary reference through this differential equation. V dot is equal to kappa times delta times rho. Here, kappa is a tuning parameter. It's a non-zero, or let's say positive scalar. Rho is the navigation field, and delta is the dynamic safety margin. We start with the navigation field. The navigation field gives the answer to the following question. In what direction should the current reference change? By definition, the navigation field should satisfy some conditions. Assume that, consider the differential equation v dot equal to rho. So the solution of this differential equation, starting from an admissible initial condition, should satisfy two conditions. If the desired reference is admissible at all times, the solution of this differential equation should satisfy the constraints at all times, and the solution should converge to the desired reference. But if the desired reference is not admissible at all times, again, the solution should satisfy the constraints at all times, but this time, the solution should converge to a point denoted by R star, which has the smallest Euclidean distance with the desired reference, but inside the constraints. Okay, here assume that the red dot is the desired reference and the blue dot is the auxiliary reference. So when the desired reference is admissible at all times, what we need is just the attractive field. So probably the simplest choice for the attractive field is this unitary vector. It's a unitary vector from the auxiliary reference toward the desired reference, and we add eta here to avoid numerical problems. So when the desired reference is admissible, using this navigation field, we can guarantee that the auxiliary reference will converge to the desired reference. But when the desired reference is not admissible, we should add another term, a repulsive term, such that the constraints are satisfied and the auxiliary reference converges to a point that has the smallest distance with the smallest Euclidean distance with the desired reference. So in this case, the auxiliary reference will converge to the point denoted by R star, which has the let's say minimum distance with the desired reference. Mathematical proof for this navigation field can be found in lemma 1 of the paper. Dynamic safety margin, the second component of the ERG framework, gives the solution, gives the answer to the following question: how safe is it to change the current reference? There are several methods to formulate a dynamic safety margin. In this paper, we will use the Lyapunov theory to formulate a dynamic safety margin. Assume that this violet cross is the current state of the system, and the dashed green line is the corresponding Lyapunov level set. We know that the Lyapunov level set is an invariant set, so starting from the violet point, we will never exceed this Lyapunov level set. So here is the idea. If we can find the biggest Lyapunov level set, which is entirely contained in the constraints, and find the difference between this biggest Lyapunov level set and the current Lyapunov level set, we can use this difference as a safety measure. So here is the three-step procedure to determine the dynamic safety margin. First, at each time, we should solve this optimization problem. Gamma I, which is the biggest Lyapunov level set with respect to the constraint I, can be found through this optimization problem. In the second step, we should find the minimum of the gamma i's, and with the minimum over gamma i's. And finally, we should find the difference between this minimum and the current Lyapunov level set. Here, and we have two notes. The first one is regarding the step 1. Even though it's an optimization problem and we should solve this optimization problem at each time instant, but we know that if the Lyapunov level set is a quadratic function, or it can be lower bounded by a quadratic function, we have a closed form solution for this optimization problem. So in this case, we don't need to solve this optimization problem at each time instant. Actually, we have the closed form solution and we can just use that closed form solution. Regarding the second step, we know that even though the gamma is safe, but it might be conservative because we are considering the worst case scenario. Okay, by following the mentioned three-step procedure, we can determine the dynamic safety margin at time t. But according to the time-varying nature of the constraints, is this dynamic safety margin valid at all times? In lemma 2 of the paper, we argue that if the gamma and the constraint satisfy this inequality, the obtained dynamic safety margin can guarantee constraint satisfaction at all times. This lemma simply means that if the constraints move toward the equilibrium point, the rate of the movement of the constraints should be lower than the dynamics of the pre-stabilized system. In theorem 1 of the paper, we combine this dynamic safety margin with the described navigation field, and we show that the combination of the mentioned dynamic safety margin and the navigation field can address the problem, and the ERG developed based on these two components guarantees that the auxiliary reference will converge to the desired reference and the constraints will be never violated. In order to validate the proposed scheme, we carried out a simulation study on drones. We assume that we have a car. The car should move to the point T, then turn and continue on the other side of the road. And we have a drone that should film this movement, and the drone should move to point R, should stay at point R, and should film the turning and movement of the car. Here, the drone should fly over the road. It means that we have two time invariant constraints and should always be behind the car. So since the car is moving, It means that we have a time varying constraints as well. In order to carry out this simulation, we will use the model of an AR drone. We have identified the model for this drone in our lab, and we assume that we know the moving and turning speed of the vehicle. Here are the simulation results. The green dot line are the design reference. The dashed black lines are the auxiliary reference, and the blue lines are the position of the X and Y positions of the drone. So as you can see here, the auxiliary reference converges to the design reference, and the drone follows this path and completes the mission. Here we have also the dynamic safety margin. As you can see, the dynamic safety margin is positive at all times. It means that the constraints are never violated. In this presentation, we have seen the explicit reference governor. Two elements or two components of the explicit reference governor. The first one is navigation field, how we can build a navigation field in the presence of time-varying linear constraints, and how we can build dynamic safety margin in the presence of time-varying linear constraints. We have seen also some simulation results in drone applications. Here are some papers, some relevant papers to study, to see the details and to study the details of the explicit reference governor. Thank you very much for your attention. And if there is any question, I'd be more than happy to answer.